In this video, we are going to find all prime numbers p such that p squared minus p plus 1 is a perfect cube. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. So assuming that such a prime p really exists, then we can try to solve p squared minus p plus 1 equals x cubed, where x is some positive integer. Then p squared minus p equals x cubed minus 1, and I can factorize both sides. Now, since p is a prime number, that means it divides at least one of these two expressions, x minus 1 and x squared plus x plus 1. Of course, p can divide both, but I'll just separate the following into two cases. The first case would be that p divides x minus 1, and the second case would be that p divides x squared plus x plus 1. That would cover everything. So for this case, if p is a factor of that, then for the products on both sides to be equal, then we must have x squared plus x plus 1 on the other hand to divide p minus 1. But from this, we would have p to be at most x minus 1 and x squared plus x plus 1 to be at most p minus 1. So that means, on one hand, the quadratic expression x squared plus x plus 2 is at most p, and then at the same time this p is at most x minus 1. So we have x squared plus x plus 3, x squared plus 3 to be at most 0, but that's impossible. So that means we have no solution for this case. That means we can only find solutions from the second case, which is that p divides x squared plus x plus 1. So we can't do any bounding from the divisibility relations. So we just try to rewrite that as an equation. Let x squared plus x plus 1 to be, say, a times p, some positive integer a. And at the same time, again, we want the product on both sides to be equal. So we have a times x minus 1 equals p minus 1. Now, again, I'm going to put the two equations together. So a times x minus 1 plus 1 is equal to p, and then multiply that by a. That equals to x squared plus x plus 1. So simplifying, we have to keep expanding the left side, and we have a quadratic equation about x. So this should be minus a squared plus a for these two terms. Then we moving them to the right side, we have a squared minus a plus 1. So now we have a quadratic about x, and we're supposed to have some integer solution for x, so that means the delta, the discriminant, should be a perfect squared. That means we're supposed to have a to the power 4 minus 6a squared plus 4a plus 1 minus 4, which is minus 3, to be a perfect squared. So we have to try to find positive integers a such that this quartic is a perfect squared. Now, this expression is very close to some perfect square, which is a to the power 4 minus 6a squared plus 9. Very close to it. In most occasions, this quartic would be larger than this perfect squared. It's a squared minus 3 all squared. We have this inequality when a is larger than 3. So for most cases, we can't have this. It can't be equal to this perfect squared, but at the same time, it's always smaller than a to the power 4 minus 4a squared plus 4, because the minus 6a squared will always cover all the differences between 4a minus 3 and 4. So this minus 6a squared term would make the quartic above to be always smaller than the minus 4a, the expression that contains minus 4a squared. So for this, it always happens. So that means when a is larger than 3, we will have this quartic a to the power 4 minus 6a squared plus 4a minus 3 to be between these perfect squares. The square of a squared minus 3 and a squared minus 2, two consecutive squares. Since this quartic is between two consecutive perfect squares, the quartic itself cannot be a perfect square. So that means we only have a very few cases to check. It remains to check a equals 1, 2, and 3. We can check that one by one. When a is equal to 1, this quartic will be equal to minus 4, not a perfect squared. When a equals 2, it's minus 3, again, not a perfect squared. When a equals 3, it will be 81 minus 54 plus 12 minus 3, and that's 36, which is a perfect squared. So we can use this and go all the way back to this quadratic equation about x. So we can solve for x, given that we know a equals 3. So we have x squared minus 8x plus 7 equals 0. X is either equal to 1 or 7. But clearly we won't have a solution for x equals 1 because p squared minus p plus 1 cannot be equal to 1 since p is at least 2. So we cross that out. What remains would be 7. So in order to solve for p more quickly, we can just use this. Of course, we can also use this when x equals 1. So 7 squared plus 7 plus 1 equals 3 times p, and p equals 19. So to check, indeed we have 19 squared minus 19 plus 1 is 343, and that's 7 cubed. So our only candidate is a valid solution. So this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.